Thank you everyone for the award. I'm very honored to have received this award. And I want to thank all of the people all of the adjudicators who were involved in the process. It's a really honor for me to be awarded this award. And also I want to, of course, thank my co-authors, Gwen Flowers, my master's thesis supervisor, as well as the rest of the team. I want to kick off the project or my talk today by showing you a video of the Englacial hydrology that we studied at or a video of the lake that drained through the study that we did. And really what we're looking at here today is the Englacial hydrological system during outburst floods. So to begin with, the lake that you're looking at here is located in the Yukon, and the lake fills over the course of approximately 4 or 5 months and eventually draining. And what you can see is the lake fills up slowly. Meanwhile, the ice shelf over here is gradually lifting up and forming crevasses near the ice front. And eventually around August 17th, the lake drained critically, losing approximately 50 million cubic meters all at one time. So really what we wanted to understand was the Englacial hydrological system during this process. And the typical model for glacial lake outburst floods was developed by John Nye in 1976, where he described the subglacial flow path connecting the lake to the toe of the glacier, the rate of discharge is typically governed by the competing processes of creep closure and melt opening. And so a lot of other studies have been conducted on ice marginal lake outburst floods, specifically in Alaska and Switzerland, and they have pointed to the Englacial system, which refers to water contained in fractures or in channels within the ice structure, as a potential important element of this piece, but nobody has really done a major study of the Englacial system during these events. So that was the question that we aimed to answer in our study, which was to see what does the Englacial system do during this. What does the Englacial system do during a glacial lake filling and drainage event? So more explicitly, our research question was, what role does the Englacial hydrological system play throughout lake filling and drainage? And even more narrowly, we can define a few minor sub-objectives to answer this question. First one being, we wanted to quantify the partitioning of water stored subaerially, subglacially, and englacially. Englacially, and the reason we wanted to do this was to understand whether the Englacial system is a significant fraction, whether it's worth caring about. Secondly, we wanted to characterize the relationship between the lake glacier system and Englacial storage. So even if there is water stored englacially, is it doing anything within the system? And what is it doing? So the study area we're focusing on is in the St. Elias Mountains in southwestern Yukon, Canada, near the Alaska, USA border. And we're looking on the Kaskawel. We're situated on the Kaskawelsh Glacier. The lake is located on the north side of the glacier, and you can see here that it's fed by 3 upstream tributaries, tributary glaciers, I should say. And the watershed that fills towards the lake is delineated in yellow here. You can, for the most part, it's defined by the topography, but on top of the glacier here, it's defined based on estimates of subglacial hydraulic potential from ice penetrating radar data collected in a previous year. So now I'm going to zoom into the lake area and try to give you a sense of what some of the instrumentation that we installed to study this outburst flood event. So we had a lake level pressure sensor installed in the lake, that's indicated by the yellow star here, as well as an entire instrument array display, or an array of instruments installed on the ice that connected a hypothesized subglacial flow path that connected an outlet tunnel that had been observed in the glacier, so that's located about here, with a potential ice dam located downstream. That's the saddle point in the subglacial hydraulic potential there. And what we did here is we had englacial water pressure sensors installed at each of these stations on the ice, as well, and this was to measure, they were buried they were drilled into boreholes about 13 meters deep to measure water pressure throughout the event. And I should note that the ice shelf itself adjacent to the lake was about 200 meters thick near the ice front and deepening to a depth of approximately 600 meters downstream. At two of the stations, we had what we referred to as primary stations or super stations. We had water pressure sensors as well as some meteorological sensors, a GPS station to measure ice shelf uplift throughout the event, as well as a radar system to measure the Englacial hydrological system throughout the event to be able to detect a difference in reflection power at depth. Finally, we also had cameras installed on the ridges around the lake, and the main purpose of these was number one, just to inform our other sensors to understand what's going on, to look at what the weather was doing and what the ice shelf was doing. But more importantly, really what we ended up using these data for was we combined them with the feature tracking software to understand uplift of the ice shelf, as you saw in the video earlier, showing in order to characterize the displacement of the ice shelf. So here's that video again, and on the left-hand side this time what we've got is lake depth plotted on the left in blue, as well as vertical displacement at this GPS station in green, as well as the results from the feature tracking software at that particular point. So I'm going to turn this video on, and what I want to draw your attention to is the fact that the lake really lifts up early on in the process, and then you have these very large fractures form on the ice shelf. The lake reached a maximum depth of about 72 meters before draining relatively rapidly, and further back from the ice shelf, we had a displacement of about 3.5 meters at this GPS station. And as you can see, the feature tracking software and the camera measurements do a fairly good job of representing the displacement measured by the GPS. So taking this a little bit further, we tracked approximately, I can't remember how many points off the top of my head right now, 30 or so points on the ice shelf in order to estimate displacement across the entire glacier. And of course, we needed to interpolate this a little bit in order to get some better estimates. But what we found was that there's about 3.5 meters of displacement further away from the ice shelf, and about a maximum of 28 meters of displacement near the ice front. These results are important for two different reasons. Number one, because you can actually visualize what's happening on the ice shelf. But more importantly, we can also use these data to estimate how much water is stored beneath the glacier by differencing the displacement of the ice shelf. So in order to do this, what we did, or in order to evaluate, to come back to our research objectives, we wanted to understand how significant the Englacial portion is. So to do this, we conducted a water balance, a fairly simple water balance calculation. And that is saying that effectively the total input volume into the system, and that's the lake and the catchment that drains toward it, total inputs are equal to the total stored volume up until the lake drains. So inputs include the initial volume of the lake plus melt and rainfall, minus any sort of evaporation from the lake, losses due to groundwater. And in terms of the stored volume, we have 3 different reservoirs that we treat as the lake in order to parse out what the Englacial component is. And that's the subaerial lake, which is what you can actually see, the subglacial system beneath the glacier, as well as the Englacial system contained in fractures, channels, maybe even between ice grain boundaries. I should also note that a big assumption of this calculation is that we're assuming that there's no leakage before the lake drainage, which is entirely possible, but will have to remain a limitation of this calculation. Secondly, we also ignored evaporation. It's fairly safe to assume that it's relatively low in this part of the world. And also groundwater we neglected. It could be a major component, but we really don't have any data. So once again, it's a limitation of this study. Here's the results from that from that analysis. In terms of the initial volume plus melt and rainfall, were driven by an enhanced temperature index model, which was driven by data downscaled from the North American regional reanalysis data set. And just to note, Julia, your presentation was really inspiring. It would have been great to have your melt model in this, maybe, or at least your snow model in this. So yeah, so we can see that the amount of water that is input into the lake early in the season is increasing up to a peak volume of approximately 50 million cubic meters in the middle of August. And we can get these error bounds that are shown on the graph based on a Monte Carlo simulation by varying the parameters that feed the model by a reasonable range of values. So secondly, we can also calculate the subaerial volume fairly simply by looking at the lake level as well as the hypsometry. We had a DEM of the empty lake, so we can estimate the subaerial volume fairly accurately. And what we found was really interesting was that the subaerial volume only accounts for about 20% of the total volume in the lake beforehand, before drainage, I should say. So the next thing we wanted to do then, of course, was to look at the subglacial system. So we could take those measurements of displacement of the ice shelf and difference them from the initial ice position to estimate the volume underneath the glacier. Using these data, we estimated about 42% of the water could be stored beneath the glacier. And so this leaves the 38% of the lake volume unaccounted for. And so that's how what we do here, what we're using, or what we're sort of concluding in this study is that there must be a fairly significant fraction of the Englacial system, a fraction of water stored in the Englacial system prior to lake drainage. So coming back to our research objective, that answers the first one that we wanted to talk about, which is to quantify the partitioning of water stored in the Englacial reservoir, specifically by parsing out the subaerial and subglacial components. And what we found is that the Englacial system does make up a volumetrically significant portion of catchment storage. Secondly, we wanted to characterize the relationship between what we want to do now is characterize the relationship between the lake glacier system and Englacial storage. So what I'm going to do now is walk you guys through a lot of the other sensor measurements that were on the glacier. On the left-hand side, I'll be throwing up all kinds of different plots of reflection power from the radar data, water depths, water pressure measurements as well. And on the right-hand side is our conceptual model interpretation of these measurements. So what we're looking at here is the lake on the left with bedrock shown below, and this is what the glacier actually looks like adjacent to that. And this section is accurate. We did a number of ice penetrating radar surveys to understand exactly what the bed looks like beneath the glacier. And on top here are the sensor positions on the ice shelf. So the first thing to note is that we had an interesting drop in the lake level in early July, and coming back to the time-lapse video, you can see that the lake initially overtops the ice front, which is interesting because obviously ice should float, and the fact that the water is overtopping the ice suggests that perhaps the ice was sort of stuck to the bed initially. So what we're inferring here is that this event sort of is kind of we're comparing it to a sort of sticky valve sort of situation where the ice is stuck to the bed and then the water overtops it and eventually sort of pulls it off. So it suggests that there's some sort of cohesive force holding the ice to the bed up until the lake has enough pressure or can exert enough stress on the ice to lift it up off of the bed. In our conceptual model, you can think of it this way by saying, okay, here's our ice front, the lake is over the glacier, but then the water level goes down as the ice shelf lifts up and water is injected into the subglacial system, or the subglacial water wedge, or the subglacial reservoir that we referred to beforehand. So next, we had another similar event in mid-July. Once again, you can see the lake depth is dropped a very small amount again. And more interestingly, you can see that in our front row of sensors, so that's these ones right here, we saw an abrupt, an inflection in the surface uplift of the glacier. Secondly, we also saw that there was an increase in the reflection power at depth. So that suggests that we have an increased amount of water in the deep Englacial fracture network. Coming to the conceptual model, we can see that the lake depth goes down again, ice shelf moves up, and water is injected further into the subglacial reservoir as well as into the deep Englacial reservoirs. So once again, you have this sort of event where the glacier is sort of peeling off the bed, fracturing, and water is being injected into the subglacial and Englacial reservoirs. Once again, we have another similar event in early August. This time we can see the data in a lot more sensors. You can see that we had a very small decrease in the surface in the water level, as well as inflection again in the surface uplift near the lake. So that's this gray one. Next, a little bit further from the lake, we have a more surface uplift noted on from the feature tracking software and the photos. Further, we can also identify an event, a very clear sort of change in the Englacial water pressure measurements that we had installed in the boreholes. So you can see that these sensors all of a sudden are either dropping in pressure or increasing in pressure, suggesting a major rearrangement of Englacial waters in the ice shelf. So this is how we start to infer that there's a lot of fractures forming. Finally, we also saw a decrease, well, not quite finally, but we also saw a decrease in reflection power near to the lake. So that suggests that perhaps we have so many fractures that water is penetrating deeper into the ice. Because remember, those borehole pressure sensors are only 13 meters deep. Whereas further from the lake, we see an increase in reflection power. So looking at our conceptual model, we can say all the same things. We've got uplift of the ice shelf, decrease in the actual lake level, decrease or a sort of drainage of the near surface Englacial system, and a further injection of water further along in the subglacial system as that ice shelf lifts up. And finally, we also have water injected up into the glacier, at that fracture network at depth, which is resulting in that increased reflection power at depth measured in our stationary radar system. So once again, what we can say here is that we have, with uplift and fracture, the subglacial and deep Englacial reservoirs are expanding outward from the lake. So once again, it's that analogy of the glacier sort of peeling off of the bed and filling with water, both subglacially and englacially. Finally, we also have the actual lake drainage event, which occurred in late August. We can see that the rapid drainage, it started as sort of a slow leak, followed by rapid drainage. And we can't really necessarily put our finger on exactly when the lake did start to drain, because of course it could be a very slow leak that was competing between the lake inputs and outputs. But what we can say is that we saw the ice shelf drop rapidly, as well as the water level in the lake drop rapidly following around August 17th. Towards the end of the season, we have very low or almost zero borehole water pressures. So that suggests that the near Englacial system is draining rapidly. And in terms of our radar system, what we measured was a dynamic response in Englacial storage near to the lake. So obviously, while the lake is draining, water is really getting pushed around between fractures as that ice shelf is bending and flexing in response to the lake level dropping. So really what we can say here is we have drainage from all three of the reservoirs, or from the subglacial and subaerial reservoirs, as indicated by the lowering water level and the lowering ice shelf. Whereas in the Englacial system, there's a dynamic response as it's going up and down, as indicated by the reflection power from our radar system. So once again, in the conceptual model, you can see we have a drop in lake level, drop in the ice shelf, drainage throughout what we presume is a subglacial flow path, based on the speed at which the lake drained. We can also see that the near surface Englacial system is largely drained, and the deep Englacial system is exhibiting a dynamic response. So finally, what we also noted was the lake did start to refill a little bit, slightly at the end of the season. And so when we look at the images, you can see by the 6th of September, it was empty, whereas shortly thereafterwards, it started to refill. The ice shelf remained grounded throughout this period, whereas we did measure an increase in the reflection power following the drainage event deep in the ice. So that's down here. I don't have a good plot to show that right now, but in the conceptual model, you can imagine that we have an increase in the amount of water content in fractures at depth in comparison to early in the season. And since the ice shelf is grounded, what we infer here is that there's a lot of fractures at depth that are storing water englacially following the drainage event that maybe weren't there early in the season. So what we can say is that with the termination of the outburst flood, we had a refilling of the subaerial and deep end glacial reservoirs. So coming back to our research objectives, we wanted to characterize the relationship between the lake glacier system and englacial storage. And what I'd like to be able to assert here from our study is that rising lake levels lead to ice shelf flexure and fracture, which causes a redistribution of deep englacial storage. So that means that the englacial system is really responding to the changing ice shelf and lake depths, or to the rapidly draining lake and the flexing ice shelf. So this is all well and good, and that's a lot of data, but I want to come back down to earth a little bit and talk about what are the implications of this study. Firstly, what we learned was that there are significant volumes of water stored englacially and subglacially. And so glacial lake outburst floods are a serious hazard across, especially in high mountain Asia, and neglecting the englacial and subglacial components in evaluating the potential for these drainage events to happen and the potential magnitude of these events could lead to an underestimate of the hazard posed by these lakes. Secondly, we also have found that there's direct evidence of, we've also identified direct evidence of dynamic, deep and shallow englacial storage. So that suggests that once these events start to drain, perhaps we need to adjust our models a little bit to better understand how the englacial system influences flood initiation, as well as flood magnitude, which is traditionally represented through the discharge hydrograph. So to close, I will just try to answer the research question that we posed at the very beginning, which is what role does the englacial hydrological system play throughout lake filling and drainage? And what we can say is that the englacial system stores significant volumes of water in a dynamically evolving system of fractures that are influenced by hydromechanical interactions between the lake and glacier. And with that, I will thank everyone for coming and would be happy to take any questions.